Okay, so these two continued fractions here were found by Ramanujan long ago, where this number phi is equal to 1 plus root 5 over 2. And these continued fractions converge rather quickly. For example, this number here is equal to 0.284079048. And if you take only these first three convergence, you get these first digits exactly. So they converge quite fast. And in this video, we are not going to prove these, but rather we are just going to have some fun with these results. Let me just point out that this thing right over here is equal to 2 times cosine of pi over 10 minus cosine of pi over 5. And this here is equal to 2 times sine of pi over 5 minus sine of pi over 10. Right. So the very striking thing about this result is that this thing here is an algebraic number, which means that it satisfies a polynomial equation in integers, and we are going to find one such polynomial right now. So let me erase this. Right. So before we try to find this polynomial, let me just do some calculations which will be useful throughout the video. For example, 5 times root 5 is equal to root of 5 plus 5 over 2, and that's equal to root 5 plus 1 over 2, which is just 5 plus 2. And we'll be using that. And also phi squared is equal to 1 plus 2 times root 5 plus 5 over 4, which is 3 plus root 5 over 2, and that's just 5 plus 1. When you add 1 to this, it becomes this expression. So we'll be using these three simple results in the video to simplify some calculations. So now let's find this algebraic, this polynomial which we were talking about. So let me erase this. So let's put x equal to 5 times root 5, the root of this minus 5. So that's what the first continued fraction was equal to. So that x plus phi is equal to the root of phi root 5. And when you square this, you get x squared plus 2 times phi x plus phi squared equals phi plus 2. That's the first of the simple identities we just wrote. And now when you replace this value of phi in right here, you get x squared plus root 5 plus 1 times x is equal to 1. That's by replacing this phi squared here by phi plus 1 and cancelling on both sides. And so now we can rewrite this like that. So x squared plus x minus 1 is equal to minus x times root of 5. And we can now square this. So x squared plus x minus 1 squared is equal to x squared 5x squared. And you can easily expand this to find that the polynomial which we were talking about, that is one polynomial which this algebraic number satisfies, is x to the 4 plus 2x cubed minus 6x squared minus 2x plus 1 is equal to 0. So now let's just study this polynomial a little bit. So let me erase this. Right. So the first thing we notice in this polynomial is that if we replace x by minus 1 over x, we have 1 over x to the 4 minus 2 over x cubed minus 6 over x squared plus 2 over x plus 1 is equal to 0. And when we multiply this by x to the 4, this becomes x to the 4 plus 2x cubed minus 6x squared minus 2x plus 1 is equal to 0. And this is exactly this polynomial here. So we conclude that if x is a root of this polynomial, then so is minus 1 over x. But we have already shown that x equals phi root 5 minus phi is a root, and we conclude that therefore 1 over phi minus root phi over x is also a root. And now let me erase this. So since these are both roots, therefore x minus phi root phi minus phi multiplied by x minus 1 over phi minus phi root 5. If you multiply this, you get a quadratic equation which will divide this polynomial here, because both of these are factors. And I am going to leave this as a very easy exercise for you, and you can use these 3 simple identities we started with, namely phi squared equals phi plus 1 and phi root 5 is equal to phi plus 2, to show that when you multiply this out and simplify, this is actually equal to x squared plus 2 phi x minus 1. So I leave this as an exercise to you. And now, so this thing divides this thing right over here, and when you actually do the long division, you will find that so let me erase. When you actually take this polynomial and divide this by this polynomial here, you will find that x to the 4 plus 2x cubed minus 6x squared minus 2x plus 1 is equal to x squared plus 2 phi x minus 1, and the quotient is x squared minus 2 over phi minus 1. And we are, I mean, you can prove, you can carry out this long division, but we are just going to check this result. So when you multiply this out, it's x squared minus 2x, x to the 4 minus 2x, so that's an x right here, minus 2 minus 4x squared over phi, no, sorry, that's not phi, and minus, sorry, that's x to the 4 minus 2x cubed of phi minus x squared plus 2 phi x cubed minus 4 phi x squared over phi, so minus 4x squared minus 2 phi x, and that's minus x squared plus 2x over 5 plus 1, and when you actually do this sum, you find x to be 4, and 5 minus 1 over 5 is just equal to minus, so 5 minus 1 over 5 is just equal to 2, so it's just equal to 1, and then you multiply by 2, so that's x squared, that's minus 6x squared, and here you get minus 1, so minus 5 plus 1 over 5 is equal to minus 1, which gives, sorry, that's 1, and 2x plus 1, and this here is, it agrees with this here. So let me just check that. So 5 minus 1 over 5 is equal to 1 plus root 5 over 2 minus root 5 minus 1 over 2, which gives 1, right? So that's a 1 and that's a minus 1, yes. Okay, so we've just checked this. And now that we have verified this, let's, oh, all right, there's one more interesting thing we can do. So you can solve this. So x squared minus 2x over 5 minus 1 equals 0 using the quadratic formula. And what you will find is that the roots of this are x equals 1 over 5 plus or minus root of 5 over 5. And this here, if you remember what we wrote at the very beginning, we see that this one, so 1 over 5 minus root of root 5 over 5, that's equal to minus e to the minus pi over 5 times 1 minus e to the minus pi times 1 plus e to the minus 2 pi, and so on. So we conclude therefore that so I mean, in playing around, we have seen that therefore this continued fraction as well as this continued fraction, they both satisfy the polynomial equation x to the 4 plus 2x cubed minus 6x squared minus 2x plus 1 equals 0.